In this lecture, we will discuss about another topic, which is the MOSFET. So MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. So this is also a transistor. So till now we have been seeing BJT. MOSFET is another kind of transistor, and of course it was invented after BJT. Okay, so and once we have a very good understanding, once you have understood whatever we have discussed till now, understanding MOSFET is very easy. In fact, MOSFET is simpler or simpler kind of transistor compared to BJT. Okay, so all the things that we have learned, the small signal analysis, in fact, all the different configuration of the amplifiers are going to get repeated in MOSFET. Okay, there's a slight difference between the BJT and the MOSFET. So let's try to discuss the basics of the MOSFET in this lecture more in details. So as I was mentioning, the MOSFET stands for M stands for metal. Then I have the oxide, and S for the semiconductor, and the F stands for the field, E stands for the effect, and of course the T is the transistor. Okay, so the name of the MOSFET has come from its structure, definitely. So MOS means I have a metal here, okay, and then maybe I'll have an oxide here, and I have my semiconductor. Okay, okay, so this is the nature of this MOS structure. It's like a sandwich structure, right? I have an oxide in between, which is an insulator. It's like similar to like a capacitor, but of course it acts as a transistor. So I have a metal, I have an oxide, and I have a semiconductor. So this is the structure of a MOSFET. So let's go in details of how actually a MOSFET looks like and how it works. Okay. Okay. Imagine I have a block of P-type material. Okay. So this is a P-type, P-type semiconductor. Okay, so where basically the holes are the majority charge carrier, and we have electrons as a minority charge carrier that we have discussed before. So now let's focus on this cross section and try to design a MOSFET on this. Okay, basically now I will be drawing this particular cross section. Okay, we'll be seeing focusing here now. Okay, and see how we can build a MOSFET on top of that. Okay. So this is my again p-type semiconductor, or sometimes this is also called as a substrate, because this is the base. Okay, this is the base where I will be fabricating all my transistor, the MOSFET. Okay, so we will start the basic first structure of the MOS, where I will be digging two kinds of wells, or basically island kind of. This is of N plus material, N type material. So I will have another N type semiconductor. Okay, these are N type semiconductor. Okay, so this notation plus, right? If I'm using any plus, P plus, N plus, or P plus, this means that they are very highly doped relative to the doping concentration of the p-type substrate. The doping concentration of this n-type material is going to become very high. Okay, so that's why this plus is used. Okay, and of course we know that what happens to the depletion layer when I have one very high doping concentration here and less. So we know that the depletion layer is going to become outward, right, and inside it's going to become very small. Okay, so now this one, and this is my p-type, and then I'll have a this is an oxide. Okay, this is an oxide, so this is an oxide, and okay, so this is an oxide which is an insulator. This is SiO2. Okay, similar to what we have in the glass. So SiO2 is basically an insulator, and again it is from silicon. Okay, and on top of that we have our the metal. Okay, so so I have this metal, then oxide, and the semiconductor. But of course, for for different regions, especially so that the so that there is a homogeneous, like everything is made of silicon. So eventually, this metal is also manufactured using silicon itself. So basically, this silicon, it can be both N-type and P-type, is a very high dope silicon. It's a very high dope silicon. So whose conductivity is of course not as good as metal but close to metal. Okay, so of course we cannot achieve the conductivity of a metal, but this highly doped silicon, also sometimes called as polysilicon, so this is used to form this metal. So finally I have this structure where I have this metal, oxide, and my semiconductor. Okay, so this is the structure of the uh, you know MOSFET. Okay, so now let's see what happens when I apply some voltages here. Okay, let's see what happens. So let's put this substrate to ground. Okay, so whenever we are applying any voltage, we need to ground, or we need to provide a potential. Okay, so for time being we are providing the potential to this substrate, so that with respect to that only I'll be able to apply a potential here. So I'll be applying a positive potential. Okay, I'm having a battery here, and I'm applying a positive potential at this metal. Now, as soon as I start applying the positive potential here, you see this is basically, it has the this is a p-type, and we know that the majority charge carrier is the holes, but it also has the minority charge carrier as electrons, and of course the ground can supply the electrons. So what will happen is this positive potential is going to attract the electrons. Okay, attract the electrons and repel the holes. Okay, so just beneath this oxide, I'll have a good number of electrons here. Okay, so it is as if, because just beneath this oxide, it is as if this has converted into n-type substrate, right? Because just beneath it, temporarily it has become um, it has the majority charge carrier as the electrons, which is like an n-type. So this is a very, very important thing that happens in the MOSFET, that I'm applying a positive potential, and this potential is attracting all the electrons of the p substrate here, and temporarily it has become an n-type. Okay, so now if you see here, now I have my n-type here, and I have my n-type here. Okay, so and it is as if like that. I also have a temporarily n-type substrate here, right? So basically a channel is formed here, right? A channel for conduction, right? I can easily do the conduction from here, right? Previously there was no channel formed when the positive potential was not applied, but as soon as I'm applying this positive potential, then a channel is formed. Now if I just start applying some potential difference, okay, let me put this also to ground, and maybe let's apply a small potential here. Okay, small potential here, and then if I apply a small potential here, okay, so this is a positive potential, and as we know that the current flows from the positive potential to the lower potential, so we can see a current starts flowing through the channel. Okay, so this voltage, let's call it, give some name. So this is Vg. The Vg voltage, of course, we need to satisfy a certain amount of, you see, like it's not that as soon as I start applying, like even 10 millivolt, 20 millivolt, it starts forming this channel. No, it has to satisfy a certain voltage, right? It has to be greater than a certain voltage, then only the channel will be formed. So, and of course, that is around, it can be 0.5 volt, 1 volt, depending upon the doping concentration and all. The threshold voltage is can be evaluated. So the conclusion is that finally a channel is going to form when my this Vg voltage is greater than Vth. Okay, so when my channel voltage is greater than Vth. Okay, so now it's very important that we name them. Okay, so of course this voltage, let's call it to be Vd. Now if you see, this is like a gate, it's turning the channel on, and it is if the voltage is not applied, there is no channel form. So it's like a gate, right? It's controlling this channel with a channel of electrons. So this terminal is called the gate, and now if you see here, so I'm applying a positive potential here, and then the electrons are flowing, right? So electrons are flowing this side, and my current is flowing this side. So electrons are flowing this side. So basically, this island is sourcing all the carriers, right? Carriers, which is basically the electrons in this case. So it is sourcing all the electrons. So this island is called the source. Okay, this is called a source. This is called a source, or represented by the letter S. And now this is draining out all the carriers. So this is drain, represented by drain D and Vd. Okay, and of course this is my gate G, represented by gate G. Okay. Okay, so and of course when we need to ground this whole substrate, right? We need to ground or connect to some potential. So of course we cannot access towards the back side of the substrate. We access towards the top side only, and there is going to be a P plus island. So this is the same type, P type, P type. So it is just to apply the potential to the substrate, or it is also sometimes called as the bulk terminal, or B. Okay, so this basically provides potential. And now one may ask why we are going for P plus. This is some other reason. The reason is because we don't want to have an abrupt transition from the P to this metal connection, right? Ultimately, we'll be connecting to the external world through the wires. So for that, there are some other reasons which you'll learn more when you learn semiconductor devices. So basically, I want a smooth transition. So we are increasing the conductivity here, and then eventually to the metal. Okay, so this is just for a connection. So this is providing the voltage here. Okay, and of course, note that if this is not grounded. Okay, if this is not grounded, then that is also fine. We can apply another potential here, right? So, but we have to be careful. So now if you see here, this has multiple PN junctions. So I have this E, P, and N, P, and N. And what I want to make sure that these PN junctions are never forward biased. This PN junction should be always be reverse biased. That's why this bulk potential, if you see this bulk potential has to be always connected to the lowest potential in a circuit, so that any of the PN junctions that I have or that I will have in future should not be in forward bias condition. So this can be only possible or can only be achieved if I connect this bulk potential at the lowest potential. Okay, so here, and so now if you see the compared to the BJT, the MOSFET has 4 terminals now: my gate, source, and drain. Okay, and of course I have this bulk, right? And because bulk is also important, because I'm supposed to connect this one to the lowest potential. Okay, so let's summarize what we have discussed. So MOSFET has four terminals, which is basically the gate, source, drain, and the bulk. Okay, and to ensure that all PN junctions are in reverse bias, condition, bulk terminal is always connected to the lowest potential in a circuit. Okay, so this has to be followed, and this we follow actually in any circuit design, that we always try to connect this bulk terminal to the lowest potential. If lowest potential is 0, we'll be connected to 0. If it is like minus 10, then we'll be connected to minus 10. Okay, so now let's see the operation of this conduction of this current more in details. Okay, so now if you see here, observe here, you see the channel was formed when there is a minimum voltage of the threshold voltage VTH, as I was mentioning, right? It should be greater than this VTH, and where VTH is a threshold voltage. Okay, let's name it. VTH is called as a threshold. I think I hope you are familiar with the term threshold. Threshold is basically the minimum amount, right? Crossing that, we'll get some activity will happen. Okay, so this is the threshold. So after Vg has to be greater than the threshold voltage. It can be 0.5 volt, it can be 1 volt, right? Again, depending upon the doping concentration of the substrate, as well as these there are different factors on which the threshold voltage depends. Okay, and in fact you can say that in BJT also we had a threshold voltage, right? BJT start conducting only when the BBE was greater than 0.7. So that is also like a threshold for the BJT. So yeah, of course it's a little different than that, but yeah, but the concept wise it's quite similar. So now the current was conducting, but if you observe here, the potential difference, right, from here to here it is Vg, right, Vg, but now from gate to drain, the potential difference here is, this is Vg minus Vd. Okay, the potential difference is Vg minus Vd. Okay, means as the Vd increases for the conduction, okay, so as my Vd is increasing, to increase this conduction of the current, that means my potential difference between this one is decreasing. Okay, so what will happen is, so instead of having an uniform channel, something like this, my channel is going to look little taper. Okay, so it's going to become like this. The reason is because the potential difference between the gate and the source, let's call it a source. Okay, this is my bulk, this is my drain, and of course this is my gate. So let's remove this. Between the gate and the source, right, is going to become higher between the gate and the drain. So let's call this potential not just Z, it is with respect to this S. So we also sometimes call as this potential difference is also sometimes called as the VGS. Okay, so now VGS, the gate VGS is going to become greater than VGD. So that's why there is going to become this tapered kind of channel. Okay, And if VGS is equal to VGD, we know that there is no conduction of electricity, because there is no conduction of electricity. This current is also sometimes called as ID, okay, the drain current, okay. So ID, let's name it as ID. So so ID is going to become 0 if my VGS is equal to VGD. So I need to have that this VGS should be greater than VGD. Then this kind of current is going to flow. Okay, but again, there is going to be a tapered kind of channel. Okay, the channel is going to become tapered. So now the question is, how is this current? What is the how much will be this current? How do we quantify it? We are not going to the derivation of this one, so I'm going to write this expression of the current. So current is 1 by D equal to mu n C aux. Okay, we'll see what are these terms means, and we will write it down also. W by L, okay, and it is VGS minus VTH, okay, into VDS minus half VDS square. So this is the expression of the current that is going to flow. So again, what is VGS? VGS is the potential difference between the gate and the source. VTH, we know that it is threshold. VDS is potential difference between the drain and the source. Okay, so of course it is same as VD, but now suppose if the source is a different potential, then it is so with respect to the source, right? Currently it is ground, so VD is equal to VDS. S is all 0. Okay, VS is all 0, but VS can be at different potential, so the potential difference it matters, right? VGS, VDS, right? D and S, and half VDS whole square. Okay, so these are the different potentials. But then comes is, what is mu n? Mu n is, as we had discussed before, it is the mobility of the electrons. Okay, so as we had discussed in our semiconductor device discussion, C aux is the capacitance, as well as mentioning that this is like a sandwich structure where I have my metal, oxide, and the semiconductor. So C aux is the capacitance basically. Capacitance, but it is not direct capacitance, it's the capacitance per unit area. Okay, so depending upon how big this area is, so it's just it can differ, right? So instead of that, so capacitance per unit area is it's a density, basically density kind of. So what is the capacitance per unit area? And W and L are the dimensions of the W and L are the dimensions of the MOSFET. W is the width of the MOSFET, and L is the length of the MOSFET. So basically, if you see the structure, if you see the structure, if you see the three-dimensional structure, so it is something like this. Okay, so I have my substrate here. This is my L, and this is my W actually. So this is the dimension of the MOSFET. So this is my L. From here to here it's L. So let me show the L here in this diagram itself. It's my L, and W is this side. Okay, so W cannot be shown in this 2D diagram. Okay, so this is the conclusion, that finally the equation of the current that is flowing. Of course, we are not going to the derivation of this ID. Derivation is very simple, but again, we are not going to discuss. You will have a VLSI course, especially the EC students or those who want to take from the other department as well. They can take. So where this derivation of this current ID will be covered. Again, this is also a very simple derivation. It's not a big deal, but again, we are not going to go to the derivation of this one. We want to see the application part of the MOSFET. Okay, so now okay, so now we have got the current, but what happens if I keep increasing this VD, right? If I keep increasing this VD, a time will come when this will become more than VZ. Okay, so then what will happen to this channel? Okay, what will happen to this channel? Let's see more in details now. So as I was mentioning, if I keep increasing this VD, a time will come when, you know, a time will come when this the difference between the VG as this basically this voltage VG as and this VGD, okay, the difference basically the VG minus VD, okay, or VGS minus VDS, okay. So with respect to source, like, or VG minus VD, this difference between these two potential, right? Basically VG minus VD, right? Because the S is grounded, so VGS minus VD will be reaching is equal to VTH. That means the potential difference from here to here is has just reached VTH. That means just here at this point, I will not be having any channel, okay? Because we know that to get the channel, my potential should be equal, right? Just it has just start forming the the channel at this point, okay? So basically the channel has been channel is no more here, okay? And of course as I keep increasing, this VD, then the channel is going to go inside, okay? So channel is going to go inside, like this, and this region is called a pinch off region, okay? This called is the pinch off region because the channel has pinched off, okay? Okay, so this is going to happen. So after this, what will happen then? The question is, what will happen to the current? The current is will become a constant, okay? And the current will become a constant, and after this it's not going to become any more dependent on the VDS. So and this point is called the saturation region because my current is going to get saturated. It's going to get saturated, okay? It's going to become constant. So okay, before we discuss further, just let's note it down, okay? When my VDS now okay, so before we write a statement, if you see here, if I rearrange it, it is basically my VDS is equal to VGS minus VTH. So this is the boundary condition where the channel at this point has ended. That means if my VDS is greater than VGS minus VTH, this tapering is going to happen. So when my VDS is going to become greater than VGS minus VTH, okay, or even equal to, then current ID will be saturated and it is called saturation region, okay? That means my current is no more going to be dependent on the VDS, and the current ID is will be given by half mu n C ox W by L VGS minus VTH whole square, okay? So if you see here, the current is now only dependent on the VGS, okay, VGS, and it's not going to become any more dependent on the VDS. So now generally the question here is asked is, okay, if there is no channel formed, if my VDS has become large and it has come to the pinch off region, and it is going inside now, then how is the current flowing? So this is the typically question that is asked. So to answer this question, the reason how the conduction will still happen is we have not shown the depletion layer. So there is going to become a depletion layer, okay? So where the carriers are depleted, because we know that there is a PN junction and it will be outward, okay? So it will be towards the P side. So, and we know that in a depletion layer there is, and because it's in reverse bias condition, there is going to become a strong electric field, and those strong electric field is going to sweep away the current, okay? This is what we have learned even in the um, BJT case also. This is what happens, and then of course the current is doesn't become dependent or independent of the, you know, I should say that independent of the electric field or the VDS applied, and the current will only basically depend on the mm, uh, how much carriers are present, okay, and which is of course dependent on the VGS, okay. So this is how exactly it works. Of course. So just remember this, okay, because there is going to be a depletion layer and there is going to become an electric field. There's an electric field. So this electric field is responsible for sweeping away these carriers. So there is a depletion layer on the side. Okay. So I have not shown it. I don't want to go more in details of this one. So we want to quickly focus on the application part. Okay. So this region is called the saturation region. Okay. So again, the condition is that VDS should be greater than VGS minus VTH. Okay. So yeah, so let's try to summarize the different conditions of the MOSFET. Okay, and we'll see that. Okay, so summarize is so MOSFET has three regions of operation. Okay, the first one is my ID is zero. There is no current when my VGS is less than threshold. So channel has not formed, so no point, nothing is happening. So this region is also called as the cutoff region. Okay, cutoff region, and the next region is the linear region. So again, my equation of the ID is, you should remember this equation definitely. So mu n C ox W by L VGS minus VTH whole square, sorry, not whole square, into VDS minus half VDS square. So this is the case when, of course, we have satisfied this one, right? My VGS is greater than VTH, of course, and here in this case, VDS is still small. It is lesser than VGS minus VTH. And finally, I have my saturation region where the current is saturated. Okay. Then this is ID is equal to, you know, mu n half mu n C ox W by L VGS minus VTH whole square. And this is the case when my VDS is greater than equal to VGS minus VTH. Okay, so there is a boundary condition here. Okay, so now let's try to look the how a MOSFET is drawn, the symbol of the MOSFET, and see these basically these two regions, linear region and saturation region, more in details, and also try to compare this operation with the operation of a BJT. Okay. Okay. So let's see the symbol of the MOSFET. Okay. So this is the symbol of the MOSFET. This is my gate, and this is my source, and this is my drain. And of course, to differentiate between the source and the drain, an arrow is used. This arrow is basically the direction of the current. So the current flows from the drain to the source. Note that unlike the BJT, the MOSFET, you see, like the Drain and the source are analogous to the collector and the emitter of the BJT. Okay, of course, it has another terminal bulk. So generally, the bulk is not shown in the diagram. Sometimes there is also an option to show it in some other different kinds of symbol, but in this symbol particularly, it is not shown, assuming that the bulk is connected to the lowest potential. Right? If ground is the lowest potential, it is connected to the ground, or if there is some other potential, it's always connected, right? So no signal is applied on the bulk. So assuming that the bulk terminal is not shown in the symbol of the MOSFET. Of course, there are different kinds of other kinds of symbol as well, where specifically the bulk terminal is sometimes shown, but generally, for simplicity, it is avoided. Okay. So the other thing is, as I was mentioning, that the collector is analogous to the drain, and source is analogous to the emitter. And what we have seen that the doping concentration of the emitter in case of the BJT is higher compared to the collector. That's why the BJT was not symmetric. But whereas in case of the MOSFET, it is not like that. The source and drain are symmetric, and in fact they are interchangeable. Okay, um, the source and drain are symmetric and they are interchangeable. But then the question is, then how do we decide which is source and which is drain? So the source and drain are defined based on the potential. Okay, so if in case of this MOSFET, the drain will have a higher potential, so that the current flows in this direction. So the this becomes the drain and this becomes the source. Whereas if I make this at a higher potential and this if I ground it, then the current will flow in this direction, and this will become the source and this will become the drain. So this is important to remember, that the drain and source are symmetric in case of a MOSFET, and it is just based on the potential how the drain and source are defined. And of course, the source will be at lower potential, and the arrow decides the direction of the current. Okay, so now let's use this symbol of the MOSFET and let's do some characterization. Okay, so this is my MOSFET, and I have applied a potential which is basically the VG potential. My source is grounded. Okay, source is grounded. This is my gate, or sometimes best is we can call it as VGS, so that with respect to the of course the source is grounded, so I'm applying a potential VG here, VGS. Okay, and then I'm applying in the drain, I'm applying a potential VDS, again with respect to the source. Okay, okay, and we have seen the two equations, right? We have this two equation, linear region and the saturation region, and we know that this ID is the is the function, right? ID is a function. So let's try to plot this ID in different situation. Okay, so I will try to plot this ID in the y-axis. Okay, and in the x-axis we will take as VDS. Okay, so keeping the VGS constant. Okay, VGS constant, we will now vary the VDS and see how um, the ID is varying. So if you see here, the when my VDS is lesser than VGS minus VTH, it will be following this equation. Okay, it will be following this equation, and as soon as the VDS becomes greater than VGS minus VTH, it will reach to this expression, and my ID will not be varying with the change in the it will not be changing with the change in the VDS. So it will be almost like a constant. Okay, so there is no more variation of the ID with the VDS. Okay, so of course if I if I increase this VGS, then the curve will get shifted, right? Curve will get shifted to other point, and it will be something like this, right? So but the point here is we change in the we change in the VDS, it is becoming constant. Okay, so if you see this behavior is quite similar to the BJT, right? So in BJT we were also doing the same kind of plot where I was varying the VCE, right, keeping the IB constant, and I was trying to plot the IC. Okay, so we can get a similar kind of characteristics. Okay, so the MOSFET has a very similar nature of characteristics like the BJT. Only the difference is that in case of the BJT, there was a current IB that was flowing from the base to the emitter, but in case of the MOSFET, there is no current flowing, right? And the VGS, it defines the how much the current is going to flow. Okay, so yeah. So now let's try to see what are the regions of operations. So this was, as I was mentioning, this region is called the linear region. And this is called the saturation region. So the reason why this is called saturation, because the current got saturated. In the case of the BJT, it was different. This region was called the active region, and this region was called the saturation region because when the VCE voltage was very small, the carriers were saturated. Whereas in this case, the current is saturated. That's why this is called the saturation region. So it is reverse. Okay. The question is why then this is called a linear region. This is not at all a linear curve. So why it's called a linear region? The reason is when my VDS is very small, so this acts like a linear, like a resistor. So it's like a straight line when my VDS is really small. So we can, from this expression also we can see here, right? So when my VDS is very small, this square term I can easily omit, right? So then my ID becomes ID equal to mu and C aux. Okay, maybe let's write it in a in freshly. So this is called a linear region when my VDS is very small. So my ID, the square term will go away, and ID will be approximately mu and C aux W by L VGS minus VTH into VDS. So if you see the implies my VDS by ID is going to become 1 by mu n C aux W by L VGS minus VTH. And of course, since my VGS is constant, it's not changing, so the ratio between them is a constant, and this is basically the resistivity, right? 1 by this gives to the resistivity, and that's why in this region when my VDS is very, very small, so this is like a straight line, right? Because the ratio of the VDS and ID is constant, and it is going through this 0, so that's why this portion is called linear region. Although in this region it's not linear, right? But when my VDS is very small, it is linear. So that's why it's called linear region. And this is called a saturation region because the current is constant, it gets saturated. And of course, we will discuss in the next classes that there will be a slight slope, just like we have seen the case of the BJT, the early voltage. So similar kind of behavior is also there, and it can be captured by finding out the slope and including a resistor in a small signal model. Okay, so in the next class we will discuss about more in details about the small signal analysis of the MOSFET and how that small signal model can be used to design an amplifier. Thank you.